Well, thank you very much, Gabriel and John, for inviting me here. I feel like I probably have the furthest distance among the crowd from Stefan, but somehow I managed to be in the network. So I'm very proud to be invited and to be here. So you guys can guess who drew this. I did put in Malad in the prompt. So I felt like the DALL-E had some access to from the. I tried a few rounds, and this is the one I felt like had somehow access to maybe Stefan's picture, and I thought did a pretty good job. The color of the hair is not quite right, but forgive that. So my path kind of crossed. I was a pure math major, tried to make the connection at Berkeley University, and went to Berkeley to do statistics PhD. And I did my PhD, as I would say, in minimum distribution length for simplicity and model selection. Now it's called L0 regularization. And somehow I came across this paper, I think that's what I remember, this matching pursuit. And it's not going. Well, yeah, here. And then start working with actually Martin Watley's group on wavelet denoising. I went to Bell Labs for audio compression in subband. So it's kind of wavelet. I really like the simplicity and the elegance of math. And I think Dave and Ian's paper already also brought wavelet to statistics. I couldn't quite remember exactly how I came across this paper, but definitely that was something stuck in my. I don't know where we met, actually. I guess my memory is not very good compared with some of you here. And then in the 2000, really got into machine learning, boosting, sparse modeling, lasso, right? This, for me, it's a new way of doing L0 regularization, and spectral collection was mentioned in Naoki's talk. And then I got into neuroscience with Jack Gallan's group, and start really seeing all these great wavelets coming out from natural images, as Dave shown. And then we actually built, with Gallan's lab, a 3D wavelet and spot modeling, and did forward modeling, and did the first kind of called mind reading from fMRI signals back to what people are watching. And then more neuroscience, and I came across the scattering transform. And then we moved to deep learning. We kind of started our own filters, and we tried to model a higher visual area called V4 instead of V1. And for the last 10 years, has been more science, cosmology, cellular biology, and deep learning. And I always wanted to bring back wavelets. And we now have a data-driven wavelet using deep learning model, which I will present. So I put trustworthiness in the title, right? So for me, simplicity, sparsity, and a lot of interpretability. And it's also for trust building, right? All these models, I still have, I think I'm a little more optimistic than Dave. After the two words can meet and not that different, actually. But I see a lot of my approach to the digital world. It's actually quite from my pure math training. I didn't quite recognize until in Dave's talk, and feeling like that's why I want understanding. I still believe there's something more enduring than just everything fleeting. And it's really work with scientists to really confirm what you learned, and also really emphasize the whole process, for that process to be rigorous, not just the final model for building trust, right? So this is a less good-looking guy, and then the one I showed you. And I like this quote, that AI is both promising and dangerous. This is before ChatGPT and GPT-4. And then one element in all this data science work is the people, right? OpenAI has hundreds of people, and there are many, many, many steps. These are some of my former and current collaborators from science, and we make so many human judgment calls. But still, we hope something to be trustworthy and stable and reliability checked. So to struggle with what we mean by interpretable machine learning, so for my former students, we work on this paper to really try to put our heads together. We work on neuroscience, biology, and genomics. And what do we really mean by interpretation? I think one thing we add to the discussion is that you want things to be reality check, predict accuracy. Descriptive accuracy is still kind of vague, depends on the domain, and we try to bring in the audience. The interpretation has to be relevant to a problem and relevant to a human audience. So this is probably a common understanding of people we like to think that interpretability on one side and predictive accuracy and decision trees, small decision trees are interpretable, not ones with 1 million nodes. Logistic regression, small ones, and you go to random forest and go to deep learning. But what's missing in this belief, I'll show you that it's not always the case, is actually we need to really talk about a mathematical or structure matching of the method with the domain knowledge. And I think wavelet for physical sciences really is a very foundational entity for us to build on. So as I mentioned, that this is what we want to do, work with scientists, and at the same time check the process. So for the rest of the talk, actually this project on interpretable machine learning completely started by Jamie, who is a hardcore machine learner, want to do sentiment analysis. I never thought sentiment analysis was hugely important, but he was very independent, very smart, so he did. So that's what got me into interpretable machine learning. And then I pushed the team, let's do some real science. And we have a collaborator from cosmology. We try our method. Kind of work, but really care about Fourier domain. And that's here's our chance, right? We have Fourier domain, we have to go wavelet. And that's where I end up doing adaptive wavelet distillation from a ResNet model. And then we have the external study now too, one is still making, from cellular biology to see whether this adaptive wavelet distillation works for a completely different scientific problem. So that's kind of how my group approach new method development. We embed ourselves with scientists, and then in the process of solving a scientific problem, we also develop new methodologies. I think that's a lot more transferable than just think in abstract. And now I'll come back to the PCS framework, really to check a lot of stability in the process of every step of the way, especially try to be robust to human judgment calls as much as you can. So the problem faced, people already doing interpretable machine learning or interpretable deep learning at a point. Some perturbation-based integrated gradient is basically local, but it doesn't really give you any importance when you have two features. So we want to go for interactive feature importance. And this is a simple sentiment analysis model, right? The movie was good, and then you know its label is positive, and we know not is negative, good is good. But we also want to give importance for the phrase, which is an interaction. And we were able to come up with, it's called contextual decomposition, when Jamie went to Google, do an intern with Liu, and then we work on this. I won't give you details. So now we can give importance not just individual pixels, but also patches of pixels. And then Chandon Singh, who is now at Microsoft Research, Jamie is doing startup, that we're able to say that you have all these numbers floating around for any patches. It's still not interpretable because they're just numbered. Can we organize them better so that it becomes more interpretable? So we use clustering, hierarchical clustering, and also use the scores to join them. So for this more complex sentence, now you see at the bottom, you have importance measures, count to positive is more blue, red is more negative. And then for all the phrases, you can also give them importance scores. And you kind of see how this becomes positive. It's a flip, right? Before that, it's still negative, but it becomes positive. So this is tell you where the label comes from in the process. And we did a small human experiment about 11, 12 people to compare with the other methods. And the first one is really we kind of add noise to the model, keep the same label. So we have a bad model because we put a lot of noise to it. And then compare with a good model. And we ask the subject, based on the interpretation, which one is a good model. So you can see that we came ahead. And the second one is about, just based on the visualization or the interpretation, do you trust it? Right, coming back to the topic of trust. And we also kind of come ahead. But this is a small experiment. This was an Arclair paper. And then that's where I start putting my influence. I wanted to do science. Sentiment analysis is cool, but it's never the most exciting thing for me. And we were able to work with Francois Lanussi, who was a postdoc with Wusuk and his colleagues, to say, like, now we have a method, a hammer. And now there's a cosmology problem. Does it help the cosmologist? So at the time, the cosmologists already built a good ResNet. This is simulated from the Big Bang. Omega M is a very important origin of universe, a measure basically some collective mass in the beginning of the universe. And then they simulate forward to today, which is the purple image, which you can actually observe with one of the telescopes. So this is, you know the truth, and you set different parameters, omega m, can you recover that? So we know the truth. And they find deep learning beats all the previous methods. So what does it really learn, right? This is a big, and they said, we want you to look at the frequency domain because we can take care of all the interactions. We can easily go to the free domain and give also an importance measure. So this is the different frequency domains, and we can come up with a number based on our generalized version, our contextual decomposition, CD score. And this is really saying that the frequency about 0.25 is the most important. And this was informative for them, saying that the higher frequencies are not as important. They could possibly reduce because simulation, the simulation on the high frequencies, and therefore speed up things. But that's when I started saying, let's do wavelet, right? We look at scattering transform for the V4, didn't quite work. We end up using AlexNet, and we said, maybe now we can try to find wavelet. It's really Wusuk and Chandon who came out with the idea, as you can see, actually quite simple to do. And that's when I said, let's do another problem, which is the cellular biology with Gogol, Yupa Yayula, who's the Berkeley Advanced Bioimaging Center scientific director. So that was a nervous paper. So there's a term already when we got into this problem called distillation. It's like you have a big deep learning model. Can you, as a teacher, can you use the output? You now can generate as much as data. Can you use that to find a smaller, more interpretable model? So people try to shrink it to a smaller model. People also try to fit like interpretable trees or additive models. So this is called distillation. And we set a new goal. We want to distill into a wavelet. We want to use the deep learning. We come up with data-driven wavelet so that we can have interpretability in physical science problem because the local field transform property of wavelets is compression, and we also want efficiency for inference. So this is very familiar to the audience. And we went to the book of Stefan and also Mayer. And we devised a new loss function in the true spirit of empirical machine learning, try to find these wavelets. So what we have is a little crowded. So let's just unpack this. So this is given to us, weights fixed by the cosmologists. It's a ResNet, I think 155 layers or something. And then if you have a given wavelet orthogonal, there's a completely inversion. And I call this, the whole thing, the new F. So for any wavelet transform, I call this, and that enters. Eventually, I'm going to search, find a good wavelet transform. It's not exactly mathematical, but it's close enough. And then the first term says that I want to constrain this unknown wavelet transform to be kind of orthogonal. We want to minimize the reconstruction loss. And this is just saying that I'm going to use the deep learning and we didn't use our CD, it was too complex to compile, like L1 penalty on the derivative of this whole new interpretation. And the wavelet loss is the one I'll expand. So we're going to use a low pass and high pass filter representation of wavelet, and then we're going to minimize this term too. Went to the book, turned all the equations into L2 penalty. Right, this is just the high pass, low pass filter. You have all these equations, we just turn that into the penalty the term in the wavelet. More equations from the wavelet books. They're not always, some of them are redundant, we didn't seem to worry about it, we just put them together. And this is the creativity of my student. I would never think about doing this. I was too mathematical. And this is more from actually Stefan's book. That's our loss, right? We did want the wavelets to be sparse, and all these terms become penalty. And do stochastic gradient descent. Let's put it together. back to the cosmology problem, right? So when I was suggesting wavelet, actually we were told the cosmology already using wavelets for this problem. They use fixed wavelets. After the fixed wavelet, they have something called peak counting predictor, which I talked about. So this is, we just end up saying, let's just replace it by a data-driven wavelet from our methods through deep learning. So let's look at this table. So this is AWD, adaptive wavelet distillation, and we want this to be small. It's the mean square error, square root of mean square error, and this is about 1. And this is the results. Only use peak 1.6. Use fixed wavelets. There's different wavelets you get, 1.5 to 1.2. ResNet brings this down to 1.15. But we got extra 15% gain on top of ResNet. If we don't use the ResNet, we just throw away the last term, and we get 1.3. Still better than using fixed wavelets, but there's a 30% gain. So this is say somehow deep learning did something for us. In terms of number of parameters, this ResNet was not 150, I was wrong. That was 18. This is 10 to the power 7, and we took, I think, 6 layers of wavelets, and we end up with about 1,000 coefficients. So there's a 10,000 reduction of number of parameters. And then we improve the prediction performance. We thought we were going to lose, because usually people think when you interpret, things become not as predictive. And this is the optimization, right? We have 2 parameters, and this is what we picked. And if you try to interpret now, it's really saying that this wavelet is going around, try to find the contrast mass. You kind of have this artificial dip and the peak. So it's really measuring the masses and move at different scales. And then through the peak counting, that's already there for us. So this becomes saying that at least use deep learning. If we use this method on top of deep learning now, this is the shape, seems to be preferred data-driven, then that's the best way to capture the mass, which is the meaning of omega m. Then I said, oh, this is just maybe only made for cosmology. I happen to be working with Gauko on a cellular biology problem. So this is a well-known clathrin-mediated endocytosis called CME. Before I worked on the project, I didn't know that's how the cells get food or anything into the membrane. So this is outside the cell, this is inside the cell. So these little guys are the food or whatever the cell wants, and they start putting things inside to tag them, and then tag them, and then bend the cell membranes. And you have some protein called actin, like scissors, and cut it in and get the whole thing in, and then unpack, and you get the food in. So it's really smart. Actually, the COVID Delta variant was used a different process, but Omicron hijacked this process. That's how the COVID Omicron gets into the cell. I was doing neuroscience. I always thought like ion channel open and close. That was my image of how cells communicate. But actually, this is more common for other cells. It's really pack and then scissor and cut. But this process doesn't always finish. And for cellular biology who want to study this process, they want to know when this is finished. So it's called a molecular partner problem. So they collect data from the clathrin, which is they know is important in this process, and they also collect something else, which is more indicative. You cannot see, it's too faint. Whether the process finished. And then the problem present to us, can you predict the green, which is more expensive to measure, from the orange? And we tried deep learning with the video. It doesn't work. It's too vague. So we had to use a lot of understanding into the microscopy to extract the information into a time series. So this is using a lot of understanding into the lens and how the cellular biology, and then we can use deep learning. So it's just video doesn't work. So you become, in the beginning we didn't have enough data, so we did very hand-tuned features about the jump. We understand that if you have high rise of the clathrin, the orange, and it's very predictive for the completion of the grain. And when we got more data, we're able to do LSTM. That's like a recurrent neural network. And we use this kind of now off-the-shelf method developed for cosmology for this problem. And we got distilled wavelets, and we just did linear combination to predict the green signal. For this, we also gained about 10 to 15%. This is R-score, so we want it to be higher. And if you use LSTM, you get 2.23. We can raise it to 0.26. If you use fixed wavelets, you get about 0.2. And if you don't use the LSTM, you get about the same as use LSTM wavelets. So this means wavelets pretty good. They could have just done that. And from 1,000 parameters, we end up with 30 parameters. And with about 10 to 15% gain in predictive accuracy. So again, you make things more interpretable. And this is really try to capture the rise, right? We already knew that we look at the data, we have hunch to feature about the rise, but it's first like artificial depresses, a little bit like the cosmology problem, and you capture this rise, and that's very predictive. So this is in the paper, and this is a similar thing, right? It's really try to follow the sharp drop. And right now, I'm working on a project with a climate scientist, Da from UC Davis and Hazan Da from Rice, my student James Duncan and former student from Rice, and then Da student at UC Davis. So this is a completely different domain, right? I was looking for, this is supported by C3 AI, it's a consortium of people try to bring industry money for research. And I felt like the more physical science problem probably is a good fit for wavelets. So again here, the best prediction model is deep learning again. So this is a weather system. MJO means maiden Julian oscillation. Southeast Asia is about heavy rain from 30 to 60 days, and they don't have details, don't have time for details. They basically were able to use 3 variables. One is about convection, two about wind speed, and you look at about 20 degrees up and down equator, and it's like temporal and spatial process. And then they use some PCA to reduce that to the 2 dimension called RMM1 or RMM2. So empirically they validated RMM1 captures the magnitude of this MJO. And then the phase of the 2 dimension, you can have an angle, really measures the location. That's what I try to show with this little guy, right? You see it's moving. It's funny that the blue ones are the heavy rains. Usually you should do the other way, but I didn't do simulation. And this is really tell you where things are. So this is called the phase. And we use something called reanalysis data from a European organization. It's combined PDE with observational data. That's so you kind of know the truth. And why this is important? It has that impact in the tropics, right? You can have huge storms. And also that indirect impacts on the actual tropics means outside the tropic region. And that's could even have like El Nino and things like that. So it's a major weather system. And the best model we reproduce, other people did too, is a deep learning model. Use a CNN. So we're able to we set up for 60 days, we're still far. Now it's only 20 days ahead. And this is, you move around from time because this is the first principal component, the second principal component. So you kind of see where the weathers are. And you want to predict not just the amplitude, you also want to predict the location. Because location is very important. If you want to see that this certain region will be flooded, there might be preventative measures governments can take. And so you want to know where the storm will be. And this is very much, I'm just getting a result this week from, so it took a while for us to get a good deep learning going. It was took like a year. So now we try to interpret. It was not easy to get the deep learning work. And we use Lawrence Berkeley computer, but it somehow has been down, so we're only able to run one run. And we use the parameters from the cosmology project because it's an image problem. We didn't take it from the LSTM. So this is only fixed. We haven't optimized to get a more optimized wavelet data-driven wavelets. So the promising, but definitely the linear is not enough. Remember for the cosmology, we had already a method for peak counting. That's now nonlinear. And we got lucky for the LSTM. What happened, we can do a linear combination. But for this one, we try linear, it gives very poor result. So we said we need nonlinear. We first stuck a smaller deep learning model. It seemed to help, but we thought that's too much. So we end up doing kernel rich and with just a Gaussian kernel. So that's now, it's relatively interpretable. So here the result, this is a correlation. So this is CNN still better, but pretty close. And this is, root mean square error. Again, this is better. But if you do L1 error, then the method using adaptive wavelets with now the optimized regularization parameters are better. And if you look at phase, the location of the storm, we're quite a bit better already. Right? So this is very promising because we haven't really optimized the lambda 1 and lambda 2 yet. And that's what hope will. So this is just shows that it seems like the green end. Okay, so what we show that this general idea about things always have to trade off is not always the case. If you get into the good science, good matching or analytical structure, you can move this way. You can actually improve both predictive accuracy and improve interpretability, as you have seen with the 3 examples. And again, back to the life science cycle, just say we developed this PCS framework to look at the process, right? You look at deep learning. But if the data is too cleaned, then you won't generalize. We have done some work on that. Some group of students would clean with 3%, like 23% of data, then you have a problem. And documentation is a huge part of this PCS framework, stands for predictability, computability, and stability. To really look at stability across many, many human judgment calls. So we did a little stability. If we change the random starting point, we get similar wavelets. We don't want this wavelet just happen to be a particular run. But if it works, you can keep that. That's not horrible, but at least it's stable. And we do 80% of data for this cellular biology problem. Again, you have very stable results. So that's what you want to really make sure your results are stable relative to this kind of arbitrary choices. And we have software if you're interested in doing data analysis and also for simulation. And we've actually just submitted the book to MIT Press. Actually, Francis is the editor of that machine learning series. And we have a free online copy end of the year, and hope the book will come out in with my co-author, former student Rebecca Barter at Utah Medical School. And future directions, we want to try to have more experience with interpretation methods, right? And can we go mechanistic? I was talking to one of our drone students, like, can we actually use the wavelet now data-driven? In the wavelet domain, maybe we can develop something simpler, PDEs, to add to the physics. And I'm working with Hutchinson Research Center, Cancer Center. They have very low replication rate for early cancer detection. And so working on to see whether we can put PCS into the pipeline of a lot of the PI's work. And here are the references. Thank you.
Okay, so there's time maybe for one short question. So maybe one comment is about, you use Stefan's book and you seem to insist a lot on his equation, in particular orthogonality. I mean, why don't you drop these equations? I mean, could you think about,
we tried the non-orthogonal, we couldn't make it work.
So it's not stable enough to get a good result?
We tried to do overcomplete. Maybe somebody else could do it, we didn't. I think we need a little more constraints. Orthogonality give you that. I thought overcomplete would be better, but we couldn't make it work. Okay,
so have Dave say, since it's not as efficient, you just drop it, and probably the way to go.
No, I mean the empirical ML work. It works, right?
It works.
Yeah.
So, I mean, what is very interesting in what you're trying to do is you are trying to bring out this notion of interpretability, but what does it mean at the end of the day? When you have a problem which has potentially billions of variables intrinsically, is it always possible to have something interpretable? And I will say a word more. In our perceptual system, everything is unconscious. We have no interpretability. So what does it mean, interpretability? It means that at the end of the day, there is a low-dimensional model that we should be able to extract?
I think it's more for one thing for communication, right? Even you have high dimension, you might be able to find some features that eventually become something we think that we can talk about and we have an intuition about. So that's what I hope we can do, something you can discuss and communicate. And
that
maybe
means
transfer.
That these few features are sufficient to describe the phenomena, and therefore that the phenomena is intrinsically somewhere low-dimensional.
That's usually I would do implicit. If it's not in the original space, it's in the feature space. That would be my mental model for what we're after. And for if you use this for patients, right, you want to describe what's going on, and then you kind of go back to, can you have some basic concept? I mean, I'm always like simplicity, including concept and also features, and so that they are stable, they're trustworthy, and can use them to do things.
Just a word, because sometimes these explanations are stories. I mean, you ask someone, why did you do that? He will give you an explanation, and it's often not the underlying. There is a lot of psychological experiments. So you believe that there is an intrinsic scientific story, low-dimensional story in all these problems.
Yeah, I mean, you see that in PDEs, right? Physics is intrinsically manifold, right? So that's what like ultimate goal we hope to achieve. And then, as you said, there's a whole range of narratives, and sometimes even useful, even it's not completely authentic in the most rigorous sense. You just give people a sense about what your algorithm is doing. It might just build the trust. Of course, the responsibility is in the doctors, but it's completely a black box. You cannot say anything. I think that's worse than like a gray box. So I'm not saying that I'm hoping eventually do some PDE, right? That's the dream. But most of the time, you're probably somewhere in the middle. But even open the box a little bit, say a little bit, I think in a way that you can share, I think for human communications, for this model enter our lives, I think it's helpful. And then if you really want to, that's what we do in a genetic line work my group does. Is that we have this interpretable models through more random forest, so a stable version of that. And we actually do follow-up gene silencing experiment. So there, the interpretability is completely verifiable, right? Because we communicate. We cannot give the geneticists, you and Ashley's group, here's a model, you go figure. We do prediction. You go figure, decide which target you do, right? We have to come up, we say, oh, we think these two genes actually interact. And that they can actually knock things down and see whether there's effect. So in there, it's more precise. I think it's definitely needed. But other times, as you said, can be a little loose. But I still think it's better than just here's you go. It's a black box.
Yes, thanks very much.
Thank you.
Thank you, Dean.